Newton figured out gravity well enough that we would ever be able to reach the moon. Wonder if what we know about time is just the tip of the iceberg. His big idea isn't just a theory. It's like a key that might open up a bunch of the universe's secrets, revealing things we've never known or thought possible. So how does Brian Cox's fresh take change what we thought we knew about time? And what could that mean for how we see reality? Come along as we check out time itself, based on Brian Cox's new theory about time. In the huge universe, there are strange things all around us about time and gravity, the basics for how we live. Imagine a world where time gets weird, speeding up or slowing down. And what if gravity isn't what we think? That's where Einstein's theories come in. He gave us a fresh way to see the universe. Einstein's ideas from the early 1900s are the base for understanding how time acts when things move super fast. He had two big theories: special relativity and general relativity. The unique theory from 1905 totally redid how we think of time and space. It says that the physics rules are the same for everyone who isn't speeding up, no matter how they're moving. This theory gives us relativistic effects, like time slowing down under some conditions. To get your head around time slowing down, think of a light clock and a fast spaceship. A light beam bounces between two mirrors. Light speed is the same for everyone. So the light seems to go farther. For someone watching from outside, it seems like it takes longer for the light to travel that path. That time difference is what Einstein referred to as time dilation, for the moving observer compared to someone standing still. Motion changes time. Knowing how things change when moving quickly is not just a game of thinking. Scientists use machines like the Large Hadron Collider to speed up particles close to light speed. When things go this fast, we must consider time differently to get the right answers. Einstein's special relativity altered how we perceive the universe, particularly in how time changes. It's not what we expect. It says, physics rules are the same for everyone, no matter their motion. Usually, we think adding speed makes something go faster, but Einstein said there's a speed limit, light speed. One weird thing is that events that occur simultaneously for one person might not for another who's moving fast. Length can also change. Moving objects look shorter in the direction they're moving. And there's the famous equation, E=mc2, showing that energy and mass can interchange. It helps us observe how minute particles behave when zooming along, and how nuclear reactions work. Special relativity isn't just a fancy thought. GPS tech uses it every day. GPS satellites send signals while moving, so time is a bit different for them. If we didn't account for changes in time, GPS would be way off. So special relativity tells us time isn't the same for everyone. It depends on how they're moving. It's like our normal universe view is a little wrong. According to special relativity, time is fluid and not fixed. Ideas like light speed being the connection between energy and mass have been proven a bunch, but there's still more. Then comes Einstein's general relativity, which began in 1915. It dives deeper into the relationship between space and time, and how the universe's structure is connected. It dumps the old idea that gravity just pulls things together. Instead, it says gravity happens because space and time are bent. It's the natural path of objects through this curved space-time, not some invisible force. Think of space-time as a huge trampoline. A heavy thing like the Earth makes a dip. If you place a ball close to it, it rolls toward the dip, like gravity. Not a pulling force, but space-time curving. General relativity explains how planets orbit the sun, predicting how they move. It even gets why Earth's orbit is not a perfect circle, but an oval. The old idea that gravity just pulls stuff can't explain this well. Einstein's theory says space and time are comparable to a flexible fabric, twisted by heavy stuff. A solar eclipse in 1919 proved this. Sir Arthur Eddington watched how starlight bent as it passed the sun. According to the theory, the sun's weight would change the starlight a bit during the eclipse. And that's what they saw, proving the theory right. just like motion can change. Time in special relativity. Gravity messes with time too. Where gravity is strong, time slows down, more than where gravity is weak. A clock near a black hole would tick slower than one far away. General relativity gives us black holes, where gravity is crazy strong, nothing can escape, not even light. The edge of a black hole is the event horizon, and once something crosses it, it's gone. Einstein's theory has big results for the universe. First, he put a cosmological constant in his equations because he thought the universe wasn't moving. But when they found out the universe was getting bigger, he called that a major blunder. The idea of an expanding universe from general relativity is a key part of the Big Bang theory, describing how the universe started. Another important idea. Gravitational waves, ripples in space-time made by heavy things moving fast. In 2015, scientists at LIGO found gravitational waves, proving another piece of Einstein's theory. Over time, scientists have tested relativity a bunch, and it keeps passing. Whether watching starlight bend or seeing waves in space and time, general relativity is still solid. Saying gravity is false is difficult, especially because we feel it every day. In physics, folks often talk about different ideas. Some, like Brian Cox, challenge conventional viewpoints. One idea is MOND, modified Newtonian dynamics, which says gravity acts differently at slow speeds inside galaxies. Instead of needing invisible dark matter, MOND says gravity is stronger, at low speeds. Dark matter is also discussed in gravity talks, along with dark energy, to explain some things in space. Some say those aren't needed. Other theories work. Some scientists against Einstein's gravity look at new options, like unknown particles or forces that could tweak gravity. New ideas are tested hard to see if they hold up. Einstein's idea of time in four-dimensional space, where time travel is maintained at light speed, has sparked new ideas. Concepts like shortcuts and wormholes were looked at by Stephen Hawking, who believed time travel was unlikely. Testing is ongoing to see if these new theories can explain gravity well. While many things have been talked about, nothing has beaten relativity yet. Questioning gravity and the norm is key to science. It lets us learn more and understand the universe better. Gravity theories keep changing, but relativity is still the best, despite difficulties and distinctions. It explains why it performs well in tests, planetary motion, light bending, and more. So general relativity is still good because it's simple and covers a lot. Like we said, special relativity says time changes with motion. So how does that affect space travel? Space travel is tough since space is big. Einstein said light speed is the ultimate limit, and that makes star travel hard, even with tech. Think of the twin paradox. One twin stays on Earth, while the other goes zooming to a star. When the space twin returns, they've aged less than the Earth twin. They've gone into the future. Time is important for space travelers because longer trips mean greater slowing of time. If astronauts visited nearby stars, time would slow a lot, and they might age slower than Earthlings. Sounds like sci-fi, but it's relativity in action. Think about a crew traveling to a nearby star system. The trip could take years, even going fast. So how does Brian Cox's time idea interfere with our preconceived notions? What could this mean for how we see reality? Let's check out Brian Cox's new time theory and the huge universe around us. There are secrets waiting to be found, like weird stuff about time and gravity, which are super important. Imagine a world where time is strange, speeding up or slowing down. And what if gravity isn't what it seems? That's where Einstein's relativity comes in, changing how we see time and gravity. Einstein gave us a new perspective on the universe with his relativity theories. His work helps us understand how time acts, especially when moving super fast. It all started around 1900, when Einstein shared two big theories, special and general relativity. The special relativity theory from 1905 changed how we see time and space. Simply put, physics works the same for everyone who isn't speeding up, no matter how they're moving. This brings up cool stuff like a special condition that slows down time. A cool way to get time slowing down is to think about a light clock. Imagine being in a super-fast spaceship. Inside, there's a light beam bouncing between two mirrors. The speed of light is the same for everyone, so the light seems to travel a longer path. The time it takes should be the same inside and outside the spaceship. But since the path looks longer for the outside observer, time appears to slow down for the person inside. It appears to take longer for the light to complete its journey. Is this difference, as Einstein put it, a slowing of time? For the moving person, time slows down compared to the one standing still. Recognizing how things shift when they move. Fast isn't just a theory. Big machines like the Large Hadron Collider are used by scientists to make tiny bits move super fast, nearly the speed of light. In times of rapid change, we have to approach time differently in order to get things right. Einstein's special relativity changed how we see the universe, particularly in relation to time. Shifts in this way disrupt our routine thinking. The physical laws are the same for everyone, regardless of how they're moving. Unlike our everyday thinking, where increasing speed simply speeds things up faster, Einstein predicted a maximum speed, the speed of light. Another cool result is length contraction. Moving things look shorter in the direction they're moving when viewed from a still spot. Then there's the famous equation, E=mc2, showing that energy and mass can switch into each other. This is key for knowing how tiny bits behave when they move quickly, and for things like nuclear reactions. Special relativity is more than just a fancy idea. We use it every day. GPS technology depends on it because GPS satellites are moving. Time acts a bit differently for them. If we didn't account for time slowing down, GPS would be way off. Special relativity shows us that time isn't the same for everyone, and it all depends on how things are moving. So time isn't set in stone. It changes with movement. Ideas like the speed of light staying the same and the link between energy and mass have been proven many times. But there are still a number of questions. Einstein's general relativity theory from 1915 goes deeper into how gravity and the universe's shape are related. It says gravity isn't just a force pulling things together. It happens because space and time are curved. Einstein's theories about time have altered our understanding of time and space, giving us the tools to explore and predict complex cosmic phenomena. But as scientists keep pushing the boundaries of our understanding, new theories and concepts are being investigated to enhance, or even replace, some aspects of relativity. One key area where these new ideas play a role is quantum mechanics. While relativity works well on massive scales, like explaining the motion of planets or the bending of light by gravity, it struggles to explain phenomena on the quantum level, like the behavior of the smallest particles. Quantum mechanics, which governs the way subatomic particles act, operates on a different set of rules than those laid out by Einstein. For example, particles can exist in multiple states at once, and their behaviors can only be probabilistically described. In contrast, relativity deals with deterministic rules that predict exact outcomes. This discrepancy between the quantum world and the relativistic world presents a challenge for physicists seeking to unify these two models into a single theory of everything. One promising approach to bridge this gap is string theory. String theory proposes that the basic components of the universe are not points, but rather tiny vibrating strings. These strings can exist in multiple dimensions beyond the familiar three-dimensional space we experience. String theory suggests that the universe may have more than the 4 dimensions we see, possibly as many as 10 or 11. These extra dimensions are thought to be compacted, meaning they are extremely small and not observable at our scale. By incorporating extra dimensions, string theory could potentially reconcile the differences between relativity and quantum mechanics. Another concept gaining attention is quantum gravity. Quantum gravity seeks to merge the principles of general relativity with the laws of quantum mechanics. In classical relativity, gravity is perceived as the bending of space-time caused by mass and energy. However, quantum gravity proposes that this curvature might be caused by quantum fluctuations, small, random changes in a system's energy. These fluctuations could potentially be observed in space-time's fabric itself, displaying a granular structure at the smallest scales. One potential outcome of this study could be the development of a theory of quantum space-time. This could offer insights into the true nature of time and space, especially in extreme conditions, such as near black holes or during the earliest moments of the Big Bang. The study of quantum space-time might even reveal that space-time itself is not a smooth, continuous entity, but rather a dynamic, granular structure that behaves differently on the quantum scale. The concept of time itself is also being rethought in light of current advancements in physics. While Einstein's theory of relativity introduced the idea that time is not absolute, researchers like Brian Cox are suggesting that there may be additional, more complex natural layers of time. For instance, what if time doesn't flow uniformly in all places? Or what if it isn't a linear progression as we experience it? Some ideas propose that time could be cyclical, or even that the flow of time might be an illusion, a result of how our minds perceive the world. The exploration of these ideas may have significant repercussions, not just for physics, but for our understanding of consciousness, the arrow of time, and the nature of reality itself. In fact, some physicists are investigating the possibility that time may be emergent rather than fundamental. In this view, time arises as a result of more fundamental operations, like the interactions of particles at the quantum level. If time is emergent, it might not be a constant backdrop against which events unfold, but rather something that arises from the underlying dynamics of the universe. This would challenge the classical view of time as a linear progression and could open up entirely new ways of understanding the cosmos. Another intriguing aspect of modern physics involves the idea of parallel universes, or the multiverse. According to some quantum mechanics interpretations, every possible outcome of an event could occur in a separate parallel universe. This idea was proposed by Hugh Everett in the 1950s and has gained traction in recent years. If true, this could mean that there are an infinite number of universes, each with its own version of time. Some universes could be very similar to ours, while others might be radically different. The study of parallel universes could lead to new insights into the nature of time, as well as the fundamental building blocks of reality. Even concepts that were once purely speculative, like wormholes and time travel, are being taken more seriously by physicists. While Einstein's theory of relativity allows for the mathematical possibility of wormholes, shortcuts through space-time, which could theoretically connect distant parts of the universe, there is still a lot to learn about how they could actually exist. Some researchers believe wormholes could allow for faster-than-light travel, possibly opening the door to interstellar exploration and time travel. However, the practical challenges of creating or stabilizing a wormhole are immense, and many questions remain unanswered. One of the big unknowns when it comes to understanding time and gravity is the role of dark matter and dark energy. These mysterious substances are thought to make up most of the universe, but they remain largely invisible to us, detected only through their gravitational effects. Understanding how dark matter and dark energy interact with space-time could be key to solving the more complex mysteries of time and gravity. Some scientists suggest that dark matter may even interact with gravity in ways we are not yet fully aware of, leading to new insights into the fundamental nature of space-time. In conclusion, while Einstein's theory of relativity has given us a powerful framework for understanding the universe, there is still much to discover. As we explore new ideas in quantum mechanics, string theory, quantum gravity, and the nature of time itself, we are gaining an understanding that the universe is far stranger and more complex than we ever envisioned. Whether through brand new theories or groundbreaking discoveries, the future of physics holds exciting possibilities that could alter our perception of time, space, and reality itself. The journey is far from over,